Okay, let's see if we can learn about Simpsons rule. Yay, and there's much rejoicing. As you remember, Simpsons rule is a method of numeric integration that will allow us to approximate an integral, a definite integral, on some interval a to b of some function. Now, we would use this if maybe the function we can't find the antiderivative, or maybe we were provided data in a table. So this is a good way to use a method of numeric integration, Simpsons rule. And if you remember, Simpsons rule is a certain number of subdivisions n on a certain interval a to b. So we take b minus a over 3n, and then we take one of the first y values, and then 4 of the next, 2 of the next, 4 of the next, and we proceed all the way till the end until we take 4 of the next to last, and then 1 of the end. So the beginning and the end, there's 1, and in the middle it goes 4, 2, 4, 2, 4, 2, until we get enough. One thing being that n for Simpson's rule has to be even. We have to have an even number of subdivisions. So when we did the trapezoidal rule, it was pretty logical where the coefficients of trap came from, and they're all 2's, because the trapezoids next to each other share a base. So there was 2 of the bases in the middle, but just 1 on the ends. That was pretty logical. But the idea is where in the world does this 4 come from? So I'll kind of show you through how this works. It's a neat little proof. It's pretty sweet. It relies on the fact that Simpson's rule uses quadratic areas on a certain subdivision. So let's take this generic quadratic equation, y equals ax squared plus bx plus c, and see if we can come up with an area on a certain interval. Okay, so, ta-da! Oh, hey, look, I drew a quadratic. Okay, so let's take this parabola. So here I have this parabola, ax squared plus bx plus c, could be anything. And here's the x-axis. And let's say we have these 3 points. Okay, and let's further say that this is the origin. And let's say that this is h units away on this side, h units away on this side. So eventually, later, in a little bit, this whole area will be our subdivision number 1, like when we add up these quadratic areas, parabolic areas. But let's find the area of this region, and let's say this is negative h, let's say this is h. Okay, well, the area shaded here is just this, right? It'd be the integral from negative h to h of this quadratic. Well, we know how to do that. That'd be ax cubed over 3 plus bx squared over 2 plus cx from h to negative h. So if we plug in h, that'll be h cubed over 3 plus bh squared over 2 plus ch minus, okay, so now this would be, if we plug in negative h, that'd be negative ah cubed over 3 plus bh squared over 2, because negative squared is positive, minus ch. Okay, well, let's clean this up. Minus minus is plus, so there'd be 2 of these ah cubes over 3's, plus this minus that is gone, and 1 ch minus minus another, there'd be 2 ch's. Okay, now for fun, now here's some mumbo jumbo. Let's take this. There is some stuff in common here. So let's factor out an h, but let's also factor out this 3. If we take one of the h's out in this 3, we'd have 2ah squared left here. If we divide 3 out of 2, we would actually have 6. The h is gone, c. Okay, so again, if you want to just check this, distribute this back, here's 2/3 ah cubed, and here would be 2ch. Okay, let's remember this for a bit. Okay, now phase 2, if this is the x value negative h, well, this has some y value. If this is 0, we know this has some y value. So we could find these 3 ordered pairs, but actually these 3 ordered pairs have to match the equation. They have to work in this equation, right? Well, so if we plug in negative h, we should get this y value. Well, that'd be ah squared minus bh plus c, right? This point here, if we plug in 0, we should get y1. Well, if we plug in 0, that'd be 0, 0, that'd be c. And this y value here, y2, if we plug in h, that would be ah squared plus bh plus c. Okay, now let's go back to, remember this? I said, let's remember this from before. So let's remember this part here, 2ah squared plus 6c. All right, let's keep that in our mind. Now look at these 3 things here. If we put these 3 together, well, wait, there'd be 2h squareds here, wouldn't there? And there'd be no bh, but there'd be 2 c's. You know, it'd be sure nice if there were 6 c's. So let's do this. Let's times this by 4. And now let's take y0 plus 4y1 plus y2. So if I add these 3 things together, ding, 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 that should equal these 3 things together. Well, there's 2ah squared. There's no bh. Now there's 1 plus 4 plus 1, 6c. And so now, if we go back to this, we found the area of this parabolic shape, and this area was h over 3 2ah squared plus 6c. But what is 2ah squared plus 6c equal to? It's equal to y0 plus 4y1 plus y2. Okay, now think about Simpsons rule, b minus a over 3n. Well, wait, here's a 3, and h, that's like delta x, right? So if we make this equal to delta x, which is b minus a over n, well, this then becomes b minus a over 3n. Well, that's the one part of Simpsons rule. And look at this, 1, 4, oh wait, I thought it was supposed to be 1, 4, 2, 4, 2, 4, 1. Well, we got the 4 all right. Okay, so now let's do this. Now look at this picture. Okay, so let's pretend we have just some function, right? So here's some function. And I've divided it into different pieces. But let's take these pieces 2 at a time. And so let's take this region, d, etc. Which, by the way, is why we have to have an even number for n. But now look right here. Well, we just did this. That's this whole thing. And this here, this is the h over 3, Okay, now watch this. What about this one here? Well, these are different x values, so they'd have different y values. So this one here, there's y0, y1, y2, 0, 1, 2. This section here would be y2, y3, y4, y2, y3, y4. And here it is. Here's where the 1, 2, 1, 4, 2, 4, 1. all of these things would have this b minus a over 3n in common, right? And so here's the third one. We can take that out. And now here there's one of these y0s. There's 4 of these y1s. But now look at this. Here's one y2 from here. Here's another y2 from there. So there's 2 of them. There's just 4 of these y3s. And y4, oh, there's 1 here, 1 there. So that's 2. And so that's where the 1, 4, 2, 4, 2, 4, 1 comes from. You could go all the way to the end, and you'd have, there'd be 2 of these, there'd be 4 of those, and at the very end, there would just be 1 of these left over. So that's kind of a neat way to show where Simpsons rule comes from. And I think it's neat because it just comes from a very trivial, an area under this quadratic, which we find in general, and then use the actual function, solve for what values of a, b, and c make this true, and then plug that in. And so that's kind of a nice way to think about how Simpsons rule works and why it's 1, 4, 2, 4, 2, 4, 4, 1. Okay, bye.